Today we will have introduction to synthetic aperture radar remote sensing and its overview for different applications. Synthetic aperture radar is a form of radar that is used to create images of objects such as landscapes. These images can be either 2 or 3 dimensional representation of the object. Now when we are talking about the synthetic aperture radar, so all the radar systems, either spaceborne or airborne radar systems, are working in the microwave region of electromagnetic spectrum, and the remote sensing which is carried out in the microwave region of electromagnetic spectrum is known as microwave remote sensing, and there are several techniques coming under microwave remote sensing. And SAR remote sensing is an imaging active microwave remote sensing technique which provides high spatial resolution dataset. This is the microwave region of electromagnetic spectrum, which covers approximately 1 millimeter to 100 centimeter wavelength of the electromagnetic spectrum. This microwave band of electromagnetic spectrum is subdivided in different categories. One is K band, X band, C band, S band, L band and P band. When we will move from K band to P band, there will be increase in wavelength and decrease in frequency, and the P band will have the longest wavelength 30 to 100 centimeter, and L band will have the wavelength range from 15 to 30 centimeter. Similarly for S band, this is 7.5 centimeter to 15 centimeter. For C band, which is widely used for agricultural applications, the wavelength range is 3.75 to 7.5 centimeter, and for X band this is 2.4 to 3.75 centimeter. In spaceborne systems, spaceborne SAR systems, K band is not generally used for SAR based remote sensing. So SAR based remote sensing is carried in X band, C band and L band. Now in future there are plans to launch the satellite in S band and P band also. When we are talking about the microwave remote sensing, so microwave remote sensing includes two types of sensor. One is passive sensor, another is active sensor. Now a passive microwave sensor detects the naturally emitted microwave energy within its field of view. This emitted energy is related to the temperature and moisture properties of the emitting object on the surface. Passive microwave sensors are typically radiometers. Radiometers are the only sensors available in microwave region of electromagnetic spectrum which is working as passive sensors. All the remaining sensors are active sensors. Applications of passive microwave remote sensing include meteorology, hydrology and oceanography. The microwave energy recorded by a passive sensor can be emitted by the atmosphere, reflected from the surface, emitted from the surface or transmitted from the subsurface. Another category is active microwave sensors. So active microwave sensors provide their own source of microwave radiation to illuminate the target. Active microwave sensors are generally divided in two distinct categories. One is imaging and another is non-imaging. The most common form of imaging active microwave sensors is radar. Radar is an acronym of radio detection and ranging. The sensor transmits a microwave signal towards a target and detects the back scattered portion of the signal. In the case of radar remote sensing, radar sensor transmits their own electromagnetic pulses, and after getting interaction with the objects appearing on the Earth's surface, some portion of the electromagnetic wave is scattered back towards the sensor, and the sensor captures the back scattered portion of the electromagnetic energy to generate an image. So the whole process is known as the back scattering, and on the basis of back scatter phenomena, SAR sensors are generating images of the Earth objects. Non-imaging microwave sensors include altimeters and scatterometers. In most cases, these are profiling devices which take measurements in one linear dimension as opposed to the two-dimensional representation of imaging sensors. Radar altimetry is used on aircraft for altitude determination and on aircraft and satellites for topographic mapping and sea surface height estimation. Scatterometers are also generally non-imaging sensors and are used to make precise quantitative measurements of the amount of energy backscattered from the targets. This slide is showing the comparison between LIDAR, optical multispectral and SAR. Generally, LIDAR sensors are operated on the platform of airborne sensors. Archive dataset of spaceborne LIDAR datasets are available, and currently we do not have any spaceborne LIDAR sensor which can provide the dataset. So here LIDAR sensor is generally operated on airborne sensors. And optical multispectral sensor, these sensors may be operated airborne as well as spaceborne. Similarly, in the case of SAR, this SAR sensor can be mounted on airborne or spaceborne to do the imaging. When we are talking about the radiation, so on radiation provides the capability to the sensor to work as an active sensor. So when we are talking about the LIDAR sensors are capable to generate their own energy, then definitely LIDAR sensors will come under the category of active sensors. When the sensor will be an active sensor, then the sensor can work in day and night in both the time periods. Like in the case of optical multispectral sensors, they are passive sensors and they are working on the concept of the reflection of the sunlight from the earth's surface. So in the absence of sun, in the night time, optical multispectral sensors are not going to provide any data set. Similarly, in the case of SAR, since the SAR sensors are coming under the category of active sensor, so they can generate their own energy and they will have the night vision capability due to the active property, and we will have the data set in the night time also. So all the active sensors will have the capability to provide the data set in night time, or in another word we can say that night vision capability is available with SAR and LIDAR sensors. When we are talking about the microwave portion of electromagnetic spectrum, so LIDAR covers infrared, optical multispectral covers visual and infrared, SAR covers the microwave portion of electromagnetic spectrum. When we are talking about the wavelength and frequency, so LIDAR sensors are operated on single frequency, optical multispectral, because from the name it is clear, multispectral will cover more than one spectral band. It means that there will be many frequency ranges. Mainly a multispectral sensor covers minimum three bands of visible region and one band of infrared region. So blue, green and red, and infrared generally 4 are captured for optical multispectral. And when we are talking about the SAR, so one SAR sensor can provide the data set in one frequency, but multiple SAR sensors or multi-SAR sensors may be mounted on aircraft to get the SAR data set in multi-frequency mode. Now when we are talking about the most important property of electromagnetic waves, these are the polarimetry and interferometry. So due to shorter wavelengths used in LIDAR and optical multispectral, polarimetry and interferometry is not possible in LIDAR and optical multispectral. But the SAR sensor, due to longer wavelength and monochromatic source, it will have the potential to acquire the data set with polarimetric phase and interferometric phase. These polarimetric and interferometric properties of SAR sensors are widely used for different applications to retrieve the different properties of Earth's surface, objects appearing on the Earth's surface. When we are talking about the acquisition time, since LIDAR sensor is an active sensor, it can capture the data set in daytime as well as in night time also. When we are talking about the optical multispectral, since these are the passive sensors, they cannot collect the data set in night time. They will have the restriction to collect the data set in daytime only. When again when we are talking about the SAR's remote sensing technique. So due to the active property of SAR remote sensing, it can collect the data set in daytime and nighttime. Another comparison is there for the weather. So LiDAR remote sensing from very high altitude cannot be done in the cloudy situation, because all the radiation or electromagnetic wave which will be emitted by the LiDAR sensor will be completely blocked by the clouds. It means that in the case of cloudy situation or at the time of rain, LiDAR sensors are not going to provide any advantage or any fruitful data set of the earth object, because due to the short wavelength, LiDAR as well as optical multispectral sensors both will be blocked by the clouds. It means that during rain season or due to the presence of cloud cover in the atmosphere, these sensors are not going to provide the data set, or the data set will not be of very good quality due to the presence of cloud cover. Now when we compare the SAR electromagnetic waves, the portion of electromagnetic wave which is used in SAR remote sensing, so what we are getting, the wavelength ranges used in SAR remote sensing will have very high wavelength or very large wavelength in comparison to the cloud particle size. So these SAR electromagnetic waves or the electromagnetic waves used for SAR remote sensing can easily penetrate the cloud cover, and it can provide the data set below cloud cover also, so that it is widely used for agricultural application, particularly paddy crop, because during the paddy season most of the atmosphere will be completely blocked by the cloud. So this is this remote sensing technique is widely used remote sensing technique to extract the information of earth objects in the presence of cloud. This is the list of few famous SAR satellites. RISAT-1 is the Indian sensor which was launched in April 2012, and it provides the data set in C-band. The mean wavelength of C-band is approximately 5.5 to 5.6 centimeter. In the case of RadarSat-1, currently this is not providing the data set, but the archive data set is available to use. RadarSat-1 was Canadian satellite, and it provided the data set on C-band. Currently another Canadian satellite which is providing the data set in different polarimetric combination is currently providing the data set in C-band, which was launched in 2007. ERS-1 and ERS-2 both were the satellites launched by European Space Agency, and both were providing the data set in C-band. Another sensor was JERS, which was launched by Japanese Space Agency JAXA, and which provided the data set in L-band. InviSat was again European satellite which was providing the data set in C-band. ALOS was the sensor satellite of Japanese Space Agency, and it was operated in L-band. TerraSAR-X and Tandem-X missions are launched by DLR, German Space Agency, and COMSAT was launched in 22nd August 2013, and it is a Korean satellite and providing the data set in X-band. Sentinel-1, which was launched in April 2014 by European Space Agency, is again providing the data set in C-band. And one most advantageous property with Sentinel-1 is the freely availability of the data set. This data set is freely available for all the users. ALOS-2, which was launched after ALOS, so this was launched in May 2014, and this is providing the data set in L-band. This is the slide representing Indian SAR Earth observation missions. Now when we are talking about the radar imaging satellite mission, so RISAT-2, which was launched in April 2009, it is providing the data set in X-band. RISAT-1 It was launched in April 26, 2012. It is providing the dataset in C-band. It provides the dataset in hybrid mode, dual mode, as well as quad-pole mode. There are some future missions like NISAR. This is the joint mission which will be launched in the collaboration with NASA and ISRO. The name is given NISAR, NASA ISRO Synthetic Aperture Radar Mission. It will be launched in 2019-20, and this will be the only sensor which will provide the data set in two frequency ranges. It means that the NISAR satellite will have the potential to provide the 12 frequency dataset from spaceborne platform. One will be L-band, another will be S-band. Another missions are RISAT 1A, which will be providing the dataset in C-band, and RISAT 3, which will be providing the dataset in L-band. When we are talking about the SAR, so SAR sensors transmit electromagnetic pulses towards the Earth's surface, and those pulses are getting interacted with the Earth objects, and scattering is mainly taking place, because when we are talking about the optical multispectral, then we are going to talk about the concept of reflection of electromagnetic wave. When we are talking about the thermal remote sensing, then we are mainly focusing on the emitted energy or emitted portion of electromagnetic energy. Now when we are talking about the SAR remote sensing, then we are talking about the concept of scattering of electromagnetic wave. So SAR sensors transmit the electromagnetic pulses, and those pulses are interacting with the Earth objects, and scattering is taking place. Some portion of scattered energy will be reflected or back scattered towards the sensor, and the SAR sensor will generate the data or image. SAR data consists of high resolution reflected returns of radar frequency energy from terrain that has been illuminated by direct beam of pulses generated by the sensor. The radar returns from the terrain are mainly determined by the physical characteristic of the surface features such as surface roughness, geometric structure and orientation, the electrical characteristic which are dielectric constant, moisture content and conductivity, and the radar frequency of the sensor. Now here when we will see in the imagery, this is the high resolution TerraSAR X imagery for the Visakhapatnam port. So here we can easily observe that the water body is represented in black color. Black color is showing or indicating that very less amount of energy is returned back towards the sensor. So finally sensor is not getting any energy from this type of object, and this object is water body. It means that perfect reflection is taking place and no energy is scattered, or scattering is very less, so these objects are appearing as dark feature. Now when we are seeing about the very bright feature are representing that high amount of energy is scattered back towards the sensor, so that these features are appearing as very bright picture. So SAR in the text, as we have already seen, SAR return is a function of dielectric constant, moisture content and the conductivity, and these all are dependent on the radar frequency also, and the characteristic of the Earth object, that's such as surface roughness and the geometric structure. So here we can see that all the metallic object or the objects or the features of urban area, they are appearing as the bright feature, and the objects which are appearing as a smooth surface, like here we can see the small patches which are the gardens and parks, are appearing as very dark feature. And here we can see the road around the park, this is also appearing as very dark feature, because from the roads also there will be very less scattering, because road surface will appear as a smooth surface for the electromagnetic wave in the microwave region. And finally all the energy which is transmitted towards the road will be reflected away from the sensor, so sensor will not get any energy from the road surface also. So this road surface is appearing as dark feature. Now when we can see about the other features, like here the trees within the park are also visible, and we since this is very high resolution imagery, we can find out the minor details of the objects appearing on the earth surface. When we are talking about the interaction of electromagnetic wave, so we can understand the interaction of electromagnetic wave with this example of soil. So first example is dry soil. So when we will see the dry soil, so in dry soil moisture content will be less. So when moisture content will be less, there will be more penetration. Some of the incident radar energy is able to penetrate into the soil surface, resulting in the less backscattered intensity. When there will be more penetration, less moisture will be there, and due to less moisture and more penetration, there will be less scattering, and finally SAR sensor will record very less amount of backscattered energy, because very less scattering will occur from the dry soil. When we are talking about the wet soil, so due to increase in the moisture content, there will be decrease in the penetration potential, and finally scattering will be more. So when scattering will be more, so these surfaces will contribute high scattering in the backscattered energy, and finally the wet soil will appear brighter than the dry soil. Just when we will compare it with the optical imagery, so in the case of optical, increase in moisture content will provide the more dark tone or darker tone in the optical imagery, but here this is the just opposite case. In the case of microwave remote sensing or SAR remote sensing, when there will be increase in the wetness, so wetness will cause the less penetration, high scattering, and finally SAR sensor will receive high amount of backscattered energy. So finally we can say that wet soil will always be appearing as brighter object than the dry soil. Now when we are talking about the flooded soil, so specular reflection will take place, because water surface will behave like a complete smooth surface, and very less amount of backscattered energy will be turning back to our sensor, and finally these objects or the soil with flood or the flooded soil will appear as very dark object. When we are talking about the SAR modes, there are different modes to acquire the dataset, SAR dataset. First mode is strip map mode, another is spotlight mode, and the third is ScanSAR mode. There are different applications according to the requirement of the user. These datasets are collected, because in strip map mode we will be getting the resolution from higher to moderate resolution, and it will capture one complete strip, because SAR sensor will be focused in a particular direction, and this will be fixed, antenna sensor will be fixed, and it will acquire the data set as an strip from first point to the last point, and finally one complete strip will be covered, and it will have the moderate resolution. Generally polarimetric data set are captured in strip map mode, and people are using this data set for different applications, for the forestry purpose, agriculture purpose, and the several other purposes. Now when we are talking about the spotlight mode, so in spotlight mode we are getting very high resolution data set. Very high resolution data set from the SAR sensor is always collected in spotlight mode, because here the SAR sensor will be focused on a small area, and very high return will return back towards the sensor from the object, and during whole acquisition period, here we can see from the first point to the last point, the sensor is focused on this small area only. So due to this region, the azimuth resolution will become very high, and finally we are getting the very high resolution imagery in the spotlight mode, particularly for the urban point of view, or like for the urban application, like building detection, object detection. People are preferring to use spotlight mode dataset. Now another category is scan mode. This is also known as the burst mode. In this burst mode, SAR sensor transmit the electromagnetic pulses, and using the beam steering capability, it is covering a very large area. Now in scan mode, now when the area becomes very large, we are going to compromise with the resolution. Resolution will be coarser and the total acquired area will be very large. So for the studies which includes the land use land cover mapping or the marine applications, they are preferring to use scan-SAR mode dataset, because in scan-SAR mode dataset the swath or the total coverage of the SAR will become very large. Now after knowing the different modes of the SAR dataset, now we are going to take just an introduction of the different formats of the SAR data. So first format is the raw data. Raw data is the format of the SAR data which is collected without any processing. Raw data is the original data which is collected from the sensor. Now when we will try to visualize the raw data, we are not going to visualize any object. We will not be able to visualize any object. Why? Because raw data is simply the collection of the different responses of the electromagnetic wave or signals. Now from the raw data, there is a requirement of different type of processing steps like range compression, azimuth compression. So after doing those compressions, the first product is generated, that is known as single look complex data set. So generally people are preferring to use the single look complex data set, because to process the raw data they will require the SAR data processor. So in the absence of SAR data processor, no one will be able to process the raw data. So people are preferring to use single look complex data. This data set will have the complex property, and each and every resolution cell of the dataset will be represented by the complex number, because if the dataset will be represented by the complex number, then only we can retrieve the information of phase of electromagnetic wave at the time of interaction with the target. So first scientific product is SLC data, but due to the ambiguity, there are several ambiguities in the SAR dataset due to its geometry. So those errors can be minimized in the multi-look dataset. So users have the flexibility to directly order the multi-look dataset also, because in multi-look dataset the ambiguities due to the slant and geometry of the SAR data can be minimized. Now the fourth category is the geocoded dataset. This category is provided just because to provide the very user-friendly dataset to the users, because most of the time people are facing problem to geo-reference the dataset, and without geo-referencing the dataset there will not be any use of the SAR data. So from geocoded dataset one can easily get the information of coordinates of different objects appearing within the scene. Now the fifth category is the polarimetric. Polarimetric data is provided with the different polarimetric combinations of the SAR data, because SAR will have the flexibility to collect the data set in different polarimetric mode. Now after getting an overview of the SAR remote sensing, we are going for the different applications of SAR remote sensing. So SAR remote sensing have very wide application in different areas, including terrestrial and the earth observation. Now here we are focusing only on few of the application. One is SAR interferometry for DEM generation, and there is SAR interferometry for subsidence monitoring, and third is cryospheric or the glaciological application. SAR has very good potential to estimate the soil moisture and the structural and the biophysical parameters of the forest area, and it is widely used for crop mapping and monitoring. SAR data set is also used for flood mapping and monitoring, and this is widely used for the oil spill mapping and the ship detection. Now we are going to one by one SAR dataset for DEM generation. So generally, two technologies of the SAR remote sensing are utilized to generate digital elevation model, which is DEM. One is stereo SAR and another is the interferometric SAR. So stereo SAR uses the parallax of SAR pairs to generate the DEM, but the optical sensors have shown very good potential on the basis of parallax of SAR pair. Now interferometric SAR has shown the potential to generate the data set with different phases of two SAR images to generate the digital elevation model with very high accuracy. A DEM of large area can be generated without need of the ground control or a few control points. Now there are two examples. One, we are talking about the Fujiyama mountain, and another example we will see of the Dune Valley. So this is here the ALOS pulsar dual polarimetric combination of the data set was used. Both the data sets were collected in the repeat pass mode, in the interferometric mode. So here both the data sets, one was collected on 1st July 2007 and another was 16th August 2007. Now we can easily see when there is change in elevation, this particular cursor, the location of the cursor is showing the Fujiyama mountain. So due to the change in the elevation, we can easily see the change in the fringes, change in the color of the fringes. This is an interferogram generated from the SAR interferometric technique, and each fringe is representing the change in the elevation or change in the phase due to the elevation, and two-dimensional representation of digital elevation model for the Fujiyama mountain is shown here, and the height is ranging from 24.4 to 3783.3 meters. Now the third picture is representing the digital elevation model and its three-dimensional surface view. So here we can easily see very high height is represented, or high height is represented in yellow color, and dark color is representing like dark green, and blue color is representing the low height. So here minimum height observed for this area is 24.4, and maximum height observed for this area, for particular for the peak of the mountain, is 3783.3 meter. And one more pattern we are observing, like for the water bodies, since water bodies are not stable structure and they are not the permanent scatterers, so we are not going to get any information of the water body either in this image or in the interferogram. We are not getting any systematic pattern of the interferometric fringes. And when we are seeing in the 3D visualization of the DEM using color background of the TM dataset, Landsat TM dataset, here Landsat TM dataset is overlapped on the digital elevation model, and we are getting the black color for the water body, and it is not showing any height. Now this example is the 3D surface view of Dune Valley. So again this is generated using the ALOS pulsar dataset, and here you can see the values are ranging from 212 to 2980 meters, and minimum height is represented by blue color, and the maximum is 2980, and all the objects and the features, they are represented according to their height. So here we can see that for the valley region we are not getting very high height, and for the undulating terrain they are clearly visible from the feature. Also we can get very good information in 2D as well as in 3D for the different objects, and in the 3D visualization we are able to clearly see the undulation of the terrain. This is the hilly terrain of the Dune Valley, we can easily see, and Shivalik range, it is also clearly visible from the imagery as undulating terrain in the 3D. Now another wide application of SAR interferometry is subsidence monitoring. So generally in subsidence monitoring, very high or precise interferometric processing is adopted. Most of the time people are using differential interferometric SAR technology to do subsidence mapping and monitoring, and with the help of differential SAR interferometry we will have the flexibility to get the accuracy in the millimeters. Generally we can get up to half of the wavelength, but very precise processing may provide the very high accuracy in the measurements for the subsidence mapping and monitoring. And interferometric SAR interferometry technique is good for monitoring the construction sites such as the mining area, city, and it can help in predicting the hazards such as the mining exploitation. Now this slide is showing the subsidence mapping of Jharia coalfield. This study was carried by Dr. Tajdar Arul, and here we can see the first image is showing the subsidence map obtained from differential SAR interferometry, and the second image is showing the field survey of the subsidence map. So in the field survey we can easily see like the white color is representing the upliftment that is ranging from -10 mm to 0 millimeter, and subsidence is ranging, which is represented in blue color, it is ranging from 0 millimeter to 10 millimeter, and the high subsidence from 10 millimeter to 27.8 millimeter is represented in the red colors. This is the field data collected for the study area Jharia coalfield, and a subsidence map with the help of differential SAR interferometry of Invisat SR data C band was excuse me, was generated, and we can easily see we are getting the subsidence from 28 to -25 millimeter. Average displacement value ranges between -25 millimeter, that is showing the upliftment, and the 28 millimeter subsidence. Another wide application of SAR remote sensing is for cryospheric or glaciological applications. So SAR remote sensing may be used for snow density mapping, glacier mass balance estimation, snow equivalence and snow depth retrieval, glacial movements, sea ice monitoring. So in this slide we are seeing the glacier mass balance estimation with the help of our Indian satellite RISAT-1 for Chota Sigri glacier. So the mass balance was estimated with the help of C-band SAR data set, and the obtained values was -0.71. Differential SAR interferometry can be used for to detect the movement in the glacier also. With the help of SAR interferometry, because SAR interferometry is used for the phase of SAR interferometry is used for the height estimation, and the same phase may be converted for the displacement mapping and monitoring. So here the movement or even the velocity of the glacier can also be known, but the requirement of the data set should be in high frequency or in high repeativity, because if the repeativity will not be high, then it might be possible that the phase information which is a function of a similar type of object, phase information will be completely corrupted, and people will not be able to find out any fruitful information. Because when we are talking about the very large interval between the two SAR passage or between the two SAR acquisitions, if the interval will be very large in several days, like 15 days, 20 days, 30 days or 45 days, then it might be possible that due to the movement of the top surface, the whole surface will be changed, and finally phase information will not be preserved and interferometry will not be possible. So if the data set will be available with very high repeativity, like here in this case, in this example, ERS data set of 1 day interval was used. So here the difference in the fringes, slight difference in the fringes may be correlated with the shift, and finally the shift in the top surface can be easily calculated. Now the maximum value calculated for in this example is approximately 0.6 centimeter. Now another wide application of SAR remote sensing is in soil moisture content estimation. Soil dielectric constant is calculated through the SAR backscatter signals. The soil moisture content can be estimated by the soil dielectric constant. The accuracy of the estimated result depends on the SAR wavelength, the polarization used. It is useful for irrigation monitoring as well as the environmental monitoring. Now this is the NASA soil moisture mission products, and this was the first global product generated from the HH polarization, HH normalized radar cross section from the SMAP radar images. So here what we can see, like the objects which will be having less moisture, or the objects which will be having very less roughness will have very low scattering. Here the water bodies are also included, like sea surfaces, sea and ocean are also included, but for sea and ocean we can easily see that surface will be appearing as very smooth surface, and specular reflection will be taking place. So anyhow we are going to get very less back scattering from these objects, and these objects are appearing as blue color here because blue is representing very low back scattering. Now soil moisture map, when we will see for India, so we are getting approximately -15 to -5, and which is represented in a red color, and -20 to -15 is -15 and -10 is represented from light blue color to yellow and red color. So here we are getting very high moisture content because very high backscatter return is response is returned from these locations, and here we are getting for the Rajasthan area we are getting very low backscattering, which is showing that there is dry soil, and finally it will be appearing as low soil moisture, and very less scattering is occurred from those locations. Now SMAP radar images acquired from data from March 31st to April 3, 2015. Weaker radar signals, blues, reflects low soil moisture or lack of vegetation such as in deserts. Strong radar signals are seen in forest. SMAP's radar also takes data over the ocean and the sea ice, and there we can easily see that very less scattering is returned back from the sea surface, and they are appearing as blue color. Now this study was carried with the help of 30 scenes of radar set 2 data over Berambadi watershed located near to located in the Karnataka state, South India. So here this is showing the change in soil moisture due to change of season and year. Here we can easily see that here soil moisture is represented in the terms of volume. So blue color is representing the maximum soil moisture and red is representing the minimum. So in the month of October 2012 and August 2012 and July 2012, we are getting very less information. As we can see in the images, very low moisture content we are getting. And in the month of this October 2011 and June 2011, July 2011 and May 2011, September 2011 we are getting very high amount of soil moisture, because here we can see that all are represented in blue color. Particularly for this watershed, it means that there is appearance of soil moisture. Now in all the 30 scenes we can easily find out the spatial change in the soil moisture and spatial behavior of soil moisture for 30 scenes of radar set 2 over the Beramadi watershed located near to the Gundalpet town in the district of Karnataka state in South India. Agriculture part of the study area shows a relatively higher variation in the soil moisture compared to the forested part. The soil moisture for the month of May-October was usually high except year 2012. A trend of decreasing soil moisture in the dry months December 2009 to February 2010 is observed, which is consistent with the fact that these months observed very low rainfall. Crop estimation is widely done with the help of SAR data set. Multi-temporal SAR data provides the information of plant growth, and it is widely used for the plant biomass estimation also. The damage area due to the flood can also be monitored and detected. The crop producing models may be used to simulate the plant to grow and predict the crop yields. Now this is an example of crop classification of agriculture crops. So here there are several crops. The green color is representing basmati, red color is representing non-basmati, yellow color is representing orchard, light blue is representing settlement, and dark blue is representing water body. Now the first image is the poly false color composite image. This was generated from the radar set 2 data set quad pole data for the October month. So here in this imagery the pink color is representing the very high scattering, high amount of scattering. Generally this is caused by the double bounce scatter, so very high amount of scattering is obtained from these objects. Green is the scattering contributed by the vegetation, particularly vegetation are the natural volume scatters, they are contributing in the volume scattering. And the blue is representing the specular reflection, mainly due to the plain roads and barren land and the water body. They are responsible for the specular reflection. Now here one classification technique was implemented to classify different agricultural crops within the agricultural area. So here particularly for this area, here we can see that basmati rice is easily detected in the green color, and the non-basmati, because here the paddy crop is mainly categorized in basmati and non-basmati, so non-basmati can be easily seen in the red color of the classification. Similarly in the second image also, here in the third image particularly, another classification approach, decision tree based classification approach was implemented, which showed high accuracy in comparison to the Wishart supervised classification. So here accuracy was achieved at 85.1%. So here also we are able to clearly distinguish basmati and non-basmati crops, paddy crops. Another differentiation was made on the basis of a scattering pattern. So here for the different phenological stages and the temporal behavior of different various polarimetric descriptors was also studied. So backscatter responses in HB polarization and the radar vegetation index was used, and again here double bounce scattering is represented in red color, volume scattering is represented in volume scattering, which is mainly obtained from the vegetation, represented in the green color, and the surface scattering is represented in the blue color, surface mainly due to the water body and the plain surfaces. Now in the first image we can clearly distinguish both the locations of basmati and non-basmati, because here we are getting high scattering in comparison to the location of basmati rice, because here there are agriculture crops and here we are getting a very less amount of the crop. Now in the second stage, yeah, definitely on the basis of a scattering pattern, here we are getting high volume scattering, and in the case of basmati we are getting mixed pattern of double bounce and the volume scattering. And again in the case of in the case of 15 September 2012, in this imagery, again we are seeing that in this imagery there is dominance of volume scattering, particularly in the non-basmati area, and mixed pattern of double bounce scattering and volume scattering is obtained for the basmati. And this is the harvested season, so we can see that this is due to the harvest there will be smooth or surface scattering or the specular reflection, so these surfaces will appear as blue color, and here due to the presence of basmati there will be dominance of the volume scattering and double bounce scattering that can be easily detected in this location. So using scattering property, one can easily distinguish the basmati and non-basmati agriculture crops. Now SAR sensor is widely used for the forest characterization. Its structural and biophysical parameters like tree height, stem volume and the biomass. So combine two separate SAR technologies, SAR polarimetry and interferometry. By combining these two techniques, one will be able to retrieve the SAR structure and biophysical parameters with very good accuracy. SAR polarimetry uses the polarization state of receiving and transmitting channels to measure the differences in the backscatter due to orientation, shape and the material composition. SAR interferometry coherently combines the signals from the two separated spatial positions to extract the interferogram. By combining two technologies, the vegetation properties such as the vegetation height and the biomass can be determined. Now these techniques, polarimetry and interferometry and polarimetric interferometry, all the high technology of SAR remote sensing are utilized in forest area, and they are also under development phase for agriculture crops also. Now this is advanced polarimetric SAR interferometry based modeling approach for forest height retrieval, and study area is the barcode forest range of Doon Valley. So now one conventional modeling approach and the modification is shown in this slide. So from the conventional approach, here we can see that dry river channels, these linear features are the dry river channels, and in these dry river channels there are stones. So due to the presence of these stones we are getting the scattering, and finally finally these are providing the error in the estimation, because when we will see, this is the height map generated for the entire study area. So this in this height map we are getting high tree height for the dry river channels also. That is the false information, because when we will see in the table, the yellow color is approximately 13 to 14 meter. So we are getting from the conventional technique, we are getting the 13 to 14 meter tree height for this dry river channel. Now after doing the advancement in the conventional modeling approaches on the basis of polarimetric SAR interferometry based modeling, now we are able to get the exact information or the more reliable information, because when we will compare the this output from the previous data set, so we are now getting the clear information that there is no height information, approximately zero height information for the dry river channels. Similarly, this is the water body from Ganga river. So here for this water body also we are getting the zero height, and this is the one algorithm is developed in our center. So this is the example of newly developed algorithm. This and the potential of algorithm was tested with the field data set, and we got a very good accuracy. Error in the tree height estimation was approximately 2.16 meter, and the average accuracy was approximately 94%. the this technique may also be used for the operational works. Now another advanced data processing for polarimetric SAR is the polarimetric SAR based modeling for above ground biomass estimation. So this extended water cloud model is developed in our center on the basis because the SAR data set in the fully polarimetric mode will have the potential to retrieve the information of different scattering elements lying within single resolution cell. So in the forest area, the scattering contributed by the top canopy, scattering contributed by the branches, scattering contributed by the stem and stem ground can be retrieved from the fully polarimetric data set. And the model, extended water cloud model, this is the extension and extension of conventional water cloud model and extension with the help of double bounce scattering, and the concept of polarimetry is included in this modeling approach, which was not existing in the early stages. So total RMSE, this was just a case study. Total RMSE was 64.12 tons per hectare in the data set, in the output of the result, and the correlation was approximately 65%. And this is example of multi-frequency Polin SAR data for the height estimation. So for the barcode forest range of the Doon Valley, this was carried, and very good result was obtained with the help of the L band LOS2 data set, X band TerraSAR X data set, and C band RADARSAT 2 Polin SAR data set. Now SAR data is since the SAR data is weather independent, it can be obtained in, before, during and after the flood event. The flood area can be mapped, the flood movement can be delineated, the flood effect can be mapped. So SAR data is widely used for the flood control also. This is an example of the case study carried for the Kendrapara district of Odisha. So there are 3 SAR images, RADARSAT 1 images acquired for the study area. So first image is acquired before the occurrence of the event, because a cyclone crossed the Odisha coastline on October 31st 1999. So this image was collected before crossing the cyclone. And now here we can see the river channels and the entire study area can be easily seen, and the existence of water body can also be seen. They are appearing, they are flowing through their proper channels, and the river channels and the water channels can be easily seen. Now after the event, after crossing the cyclone, now we can see the entire top portion is completely affected by the flood. Very high flood amount can be easily seen due to the appearance of water, and due to the appearance of water, the entire area is appearing dark, and definitely very high amount of flood can be easily detected from the SAR data set. And another image was collected on the 4th November after 4 days of the cyclone event. So after 4 days, now here we can see that now the amount of water is decreasing, and this is showing the classification of the data set. So water body is represented in white color, and non-water area is represented in blue color. So easily here we can see that there is no effect of flood before the event in the first image, the image which was collected on 11th October 1999. Now in the second imagery we can easily see that the entire area is flooded, and it is represented in white color. And after 2 days after 4 days of the cyclone, now here we can see that there is less amount of the flood water is detected here. This slide, and this is the another case study on Kosi flood and the flood extent map of Thailand. So here we can see that this is the Invisat SR data, Invisat Advanced Synthetic Aperture Radar data, which was collected during 20th August 2007. Now in the SAR imagery, the very dark portion or very dark appearance can be easily seen by the water body due to the flood, and flood extent map was generated. In this map also, the flooded area is represented by black color, so the flood extent can be easily seen from the SAR data set. And similarly, in the case of the flood extent of map of Thailand also, one can easily find out the appearance of water due to flood in the SAR imagery. SAR imagery is also widely used for oil spill monitoring. Because the SAR data set is cloud independent, oil cover surface is clearly displayed in the SAR images at the dark regions. Some softwares can detect oil spills automatically. The thickness of the oil layer may also be obtained using SAR data. With the multi-temporal data available, the source of pollution may be discovered. This slide is showing the mechanism of the sea surface backscattering. So oil films dampens capillary and gravity waves, reducing the surface roughness and the radar backscattering. Oil films appear as dark patches in the SAR imagery. Several other natural ocean phenomena such as organic films, grease, ice also dampens the wind generated short gravity capillary waves. Hence, similar dark patches in the imagery are formed. Such dark objects are called the oil spill lookalikes. Now using the polarimetric property, because in the SAR data also there will be confusion due to the look-alike element and the oil spill. So using the polarimetric property of the SAR dataset, one will be able to clearly distinguish the oil spill from the water surface. Now this is the example carried this case study is carried over the Gulf of Mexico with the help of UAV SAR dataset. Now with the help of this dataset, advanced processing was done, and two decomposition models were implemented on the dataset, and we can see here in the blue patches and with the reddish patch, we can easily identify the oil spill. Now the study also carried the utilization of different polarimetric properties of the SAR dataset, and it was found that using the polarimetric properties, one will be able to clearly identify the oil spill. Now here you can see that in geometric intensity, correlation coefficient, and fractional polarization and several other properties were used to detect the oil spill, and most of them were able to distinguish the oil spill from the background water. And one study was carried by Mr. Liu for the oil spill detection for the same dataset. Now the classification and the segmentation approach was implemented, particularly classification approach was implemented, and this was validated. Now in this classification approach, the first image was showing the result of the study from the Mr. Liu 2011, and the second and third were the study carried showing the potential of polarimetric property of the UAV SAR dataset carried in IIRS. So here in this study, what we can see that here in the classification of Liu et al, we are getting some errors. Actually these are not the oil spill, but these are misclassified as the oil spill. Now using the fully polarimetric property, we can see that we are not getting these errors. It means that fully polarimetric SAR data will have the potential to identify the oil spill with very high accuracy. Another study was carried for the North Sea with the help of UAV SAR dataset. Actually 4 experimental oil spill were released in the North Sea in June 2015, and the appearance of ships, this can be also identified as very bright patches. Now all the 4 patches were clearly identified. When we will see in the background, really it is difficult to differentiate or distinguish the oil spill from the background, but with the help of polarimetric property, there are 2 examples. One is given on the basis of Wishart segmentation of the polarimetric data set, and another is the SVM segmentation. Using both the segmentation approaches, we were able to clearly identify the patch of oil spill from its background. Now there are several other applications of SAR remote sensing, and one can implement the SAR data set to retrieve the information of the objects appearing on the Earth's surface. Thank you.